Remember that ridiculous 1980s movie, Weird Science? It's one of those John Hughes flicks about a couple of down-on-their-luck nerdy teenagers. After watching Frankenstein, the teens are inspired to try to create the perfect woman. I'm using air quotes here, by the way, by connecting a hacked computer to a doll. Much to their delighted surprise, the experiment works, and an actual perfect woman emerges out of thin air. No spoilers, but hijinks ensue, and the nerds are saved by science in the end. It makes me wonder, what if, minus the sexism and corny storyline, Weird Science was real life? But instead of a magical woman swooping in to save the nerds, supply chain uses weird science to save the world. This is Radical Reinvention, a show by 0100 about reimagining global supply chains. I'm Deborah Dole. Inventory is my favorite topic, and I've spent my career trying to figure out how supply chains can save the world. I've learned that most of the time, supply chains aren't designed around the needs of the planet or its people. So our mission at 0100 is certainly ambitious. Our goal is to create 0% carbon and 100% digital global supply chains. We believe it's possible, but we know we can't do it alone. That's why we're building a community of the world's most innovative supply chain pioneers, industry experts, and scientists, then working together to tackle some of the biggest challenges facing the planet today. And we're inviting all of you along for the ride. Join us as we work to create a sustainable and responsible supply chain, one radical reinvention at a time. For today's episode, we're digging into weird science around concepts like green chemistry and bioprinting. This kind of cutting-edge stuff has the power to completely change how supply chains source raw materials, convert them into goods, and then move them to customers. And today, we're talking with the pioneers behind some pretty incredible and groundbreaking innovations. We're going to kick things off with Colin from our research team, who's going to help us set the stage for this issue and better understand why supply chains need to be taking advantage of weird science right now. From there, I'm taking you on a little trip through each stage of the supply chain, from source to make to move. First, we'll meet Tom Van Aken from Avantium, a company that develops renewable chemistry to produce a fully degradable plastic. After that, we'll talk to two people who will help us understand just how powerful biology can be in manufacturing. Dr. Anthony Atala, the director of the Wake Forest Institute for Regenerative Medicine, will teach us a bit about 3D printing organs. Then, Eben Bayer from Ecovative is going to explain how mycelium, essentially mushrooms, is used to make both products and packaging. Finally, we'll look at some of the weird science that moves things through a supply chain. To do that, we'll chat with Tyler Cole, an electrofuels expert and host of the Net Zero Carbon podcast. And maybe if we've got just a bit of time at the end, we'll spend a little time daydreaming about what's on the horizon for weird science. All right, let's jump in. So we're starting the show with Colin Gilbert, the head of research science here at 0100. Colin, always so good at helping us make sense out of the data, and always good for some humor along the way. Welcome back to the show, Colin.
I did really think that the first episode was a one and done proposition, so I'm as surprised as you to be back here. What are we talking about this week?
Really cool topic. We're going to talk about weird science and if weird science can save supply chain. And we, of course, talk about all kinds of science all the time on our team, don't we?
All right, so I did my homework and I watched the classic 1985 film starring a young Anthony Michael Hall and Robert Downey Jr., and I'm just really surprised because I think this is John Hughes's worst film, and I'm surprised you recommended it. There is some very sexist, misogynist overtones to this film, Deborah. So where do you want to take this?
The good news is that is literally the opening of this episode, and we definitely call it out as sexist. All right, so science, why are we doing this? We have so much work to do in supply chain, of course, on the path to zero carbon. And along the way, we're expected to still be saving money and going faster and having higher quality, all the benefits that supply chains add to the organizations we support. And on top of it all, we have urgency around commitments we've made around global climate change and specifically around carbon. So, one way we can get there, of course, is to engage the scientific community. What have you been seeing on this recently, Colin?
Well, I think that the first thing we got to do is establish a little bit of context or common ground. I think every listener at some point has seen these really depressing ribbon charts of global warming scenarios. And long story short, but in lead up to the 2015 Paris Accords, we were tracking along a path to between 3.6 and 4.2 degrees Celsius change or increase in temperature by the end of this century, by 2100. And since then, that trajectory has gone down to 2.7 to 3.1 degree change, but we're still 93% above or nearly twice as warm as we want to be to get into the Goldilocks zone that scientists think is an acceptable change in global warming. And this gap between where we are and where we want to be is referred to as the ambition gap. And even if everybody hits all of their pledges and everybody hits their 2030 targets, we're still about 50% above where we want to be at the end of the day. And so I think the big question for us is what are some of the shortcuts? What are some of the innovations, especially from the scientific community, that can either change the trajectory, change the confidence interval of where we're headed, or radically change what the current ambition gap is between today versus tomorrow. But I think to get there, it's a twofold exploration. One is, of course, the innovations that we'll talk about throughout this episode. But the other, I think, is a frank discussion about where we are in terms of measurement. And Deborah, I know that you've written a lot about this recently. And it's interesting because those ribbon charts, those trajectories are based on atmospheric sensors and a lot of very well established kind of math, but they don't really go beyond what's contained in that ribbon in terms of who is responsible, what is a larger contributor, et cetera, et cetera. So, how do we know in terms of measurement what's going on below that base level of data?
This is a really tough one. A conversation we have across the 0100 community often is that, look, supply chains were not built for carbon transparency. We were built for fast and cheap most of the time. And in recent years, for high quality and a competitive advantage. And here we are now almost on a back foot thinking, gosh, we need to figure out our supplier, and their suppliers often change. Now, it doesn't escape the fact it's almost like the tree falls in the wood joke. Emissions are happening, whether we know about them or not, or where they're happening, or who's responsible for them. We have decent measures, of course, around the world, thanks to the scientific community and lots of different measurement areas set up. By country, we have okay estimates and some commitments, although none help us get to that 1.5 in entirety. As a world, we haven't spanned that ambition gap you talked about. And then it gets even harder when we start talking about individual companies or supply chains, because, of course, we're global by nature. And so, how do we know a carbon atom doesn't know where the borders are or where my factory starts and your ends? And so, it starts to get quite complicated for us to figure out this measurement. What can be helpful, though, and we'll spend more time talking about this, is to not get too caught up in this measurement challenge. We love to measure in supply chain. It's how we know what we can go and impact. And in this case, there's a lot that we can do in the meantime while we try to get our measurement figured out.
Is another way to say that is that countries or sectors or industries are actually the wrong unit of analysis sometimes for the measurement, because when you're looking at things through that level of generality, typically you come to mitigation solutions that you're deploying the same solution across everybody, even though people are on very different paths to decarbonization, indeed different point solutions at different parts of the supply chain to really accelerate forward and get the most return on investment.
Fun. I think our unit of measure in this case, or how we split that unit of measure, is a real challenge. I'd love to see supply chains get to a point where, just like we have a cost per unit, we should get to a carbon per unit or a gram per unit, some measurement, so that we can start to develop what is called a carbon intuition. Just like how when you look at a meal, you know that a big plate of French fries is more calories than a plate of spinach. That kind of intuition, as we understand the different operations we have and what causes and drives the carbon intensity of our operations, that is a great place to get to.
Taking that one step further, if we're trying to identify these killer apps for decarbonization, these emerging areas of natural or physical science that we can apply to this mammoth problem, is it better to group them into categories that are part of a system or part of a wider framework than saying this solution works for industrial equipment and this solution works for consumer goods and so forth and so on? What is an alternative framework by which to categorize weird science into kind of different categories that's more specific to supply chain?
Totally. Look, I'm sort of old school in some ways. And so when I think about supply chains and how to identify the areas that weird science can really save our processes, enhance, accelerate our progress, I think about a value stream map. So value just flowing through the different functions. But instead of the value that we think about commonly like materials, we could consider carbon to be valuable. And it is. That's what makes our soft drinks fizzy, and it's used in the medical profession, and it's used all over the place. So it's a real asset. It's an input, a material that we can use. And if we think about carbon flowing through our operations, then we can imagine something like a carbon stream map. And I think in this way, you start to understand for your supply chain, broadly speaking, which areas are the problem areas to go and tackle. Is it the raw material? Is it production? Although that's normally a series of factories. Is it the packaging? It is sometimes, depending on which supply chain you're in. And then that helps us understand where can we go and innovate, where should we go look for partners. And that's what we're going to explore in today's episode. So listen, to end our time today, probably not your time on the podcast though, because you're 2 for 2 at this point. So I feel like this is not the end of your podcast career.
No, this should definitely put an end to that.
Colin, thanks for bringing your research, science, and dare I say, charm and humor into the podcast. And we'll see you next time.
Thank you, Deborah.
So with some of that data in mind, our journey begins. We'll start with source, since that's the very beginning of the supply chain, literally. In other words, where the raw materials used to make things come from. And one big challenge we hear a lot about these days in supply chain is the search for alternative materials. This is because there often isn't enough supply of what's needed, and because so many traditional materials are pretty terrible for the environment. One company doing something really cool about this is Avantium. Now, you've probably heard about PET, a resin that's used to make plastic for everything from water bottles to polyester clothing. It's super commonly used, amounting to close to 25 million tons last year alone. It's also made of fossil fuels, which of course means it's super not sustainable. Well, one of the things Avantium has done is create a revolutionary new resin called PEF, which is completely plant-based, fully recyclable plastic product. Not only that, but the folks over at Avantium say it performs even better than fossil-based plastic. And they're preparing to open a PEF production plant in 2024. This is Tom Van Aken, Avantium's CEO.
We're developing a next generation of sustainable technologies to make chemicals and plastics out of renewable forms of carbon. So our mission is to make sure that the chemical industry and the plastics industry do not rely on petroleum as feedstock or other fossil sorts of carbon, and also make sure that they are part of the circular economy. And that requires sort of reinventing the chemical industry. We've been using plastics for 60, 70 years, and everyone is completely used to having plastics in their lives. You would be surprised, I think, if you would see how much carbon is coming into the atmosphere by producing chemicals and plastics. And that is, of course, a combination of feedstock as well as energy. And if you want to switch it to renewable forms of carbon, you have to start using agricultural commodities, you have to use plants as feedstock. So you come into a completely different type of economy. And also, of course, you then have to also make it circular. The funny thing is, if you look at the traditional plastic companies, I think they've all seen the light that plastic pollution is causing a lot of problems. So they're all trying to make it basically circular. So recycling of plastics has become a top priority. But I think they're going for a quick fix of the problem, where I think more disruptive innovation is required, looking at different feedstocks. And that's not something which is trivial, because the whole chemical industry is basically connected and is built on oil refineries. So I think the conventional petrochemical industries recognize how important it is, but I'm always amazed by how little they're really doing to make a real change here. And I think that's why you need new companies like Avantium to really come up with more disruptive and fundamental innovation in order to tackle these issues. Our most advanced product is a new plastic product called PEF. It's 100% plant-based. We don't need one drop of petroleum to make this. It looks from the surface a bit similar to PET, which is, of course, the polymer that everyone is well familiar with. But next to the fact that it's 100% plant-based, it is also something which is intrinsically better. It has much better performance in comparison to PET. It has very high gas barrier properties, so it's really good for packaging of carbonated drinks. It's also really good for keeping air out of packaging, so for things that are sensitive to oxygen. It has better heat stability. It is a product that is completely circular, so you can reuse it, you can recycle it. And if it ends up in nature, it's going to degrade more than 100 times faster than PET. We work with biorefineries, so they're buying corn and wheat and sugar beet or sugarcane from farmers and process that in different streams. We then buy their syrups and we feed the syrup into our production facility and convert it into PEF. So right now we're still working on a process that is what we call first generation sugars, so sugars coming from the agricultural industry. We're also working on second generation process that will use plant-based sugars that are coming from non-eatable types of biomass, so wood chips or agricultural waste. We certainly don't want to interfere with food supply chains. But like any chemical technology that's out there, it's going to be an evolution of different technologies that will be coming to the market. 10 years ago, we built a pilot plant, and right now we are building the first commercial scale manufacturing site in the north of the Netherlands in Delfzijl. And so this is going to be the first time that the world will see PEF coming out of a manufacturing facility, and therefore also you will hopefully see PEF bottles in your supermarket in the coming years. If you look at what we're going to be doing in that facility is we take fructose syrup as a feedstock. We run that in our chemical process. We basically first take water out and we add air, and then you come into the building block that's called FDCA. And FDCA is then subsequently converted into the new plastic. So you basically make a resin that's called PEF, and PEF is then shipped into the facilities of beer companies, soft drink companies, water bottling companies, plastic packaging companies, fiber, textile companies, and is then converted into all kinds of products where PEF can be replacing alternative plastics or glass bottles or alumina cans. That facility is planned to come on stream in 2024. So I think that's a very exciting prospect. The first plant has a 5,000 ton production capacity, which is pretty big because right now there is no PEF produced at all in the world. So this is going to be the first 5,000 tons per year that's going to come to the market. But in the world of plastics and in polyesters, that's a very small scale facility. So after that, we plan to sell technology licenses in order to enable large-scale facilities to be built using our technology. Once these larger scale facilities will come on stream, of course, we can compete in a much wider range of materials. Partnerships are really fundamental to this because if you look in the history of the chemical industry, it was more than a decade, I think even more than 2 decades ago that a new plastic was brought to the market. So as a small company to bring something like this to the market, you really depend on finding and attracting the right partners. And these are partners across the value chain. So we have created partnerships for the sourcing of the feedstock, for the plant that we're building, but also for converting the plastic into plastic products, and of course, coming to the market, working with brand owners. What we need is the existing industry to basically, instead of resisting change, is embrace that change. And they can switch over very easy. They can use their existing assets. They have to make some hardware changes, but then they can make PEF. And I think once the consumers and brand owners are embracing that, the industry will follow. And if we succeed in that system, then you will see that you have dramatic lower carbon emissions from the use of these materials. And I think that is really helping us to come to a carbon negative.
It's just super exciting, everything happening at Avantium. Being able to produce a serious and fossil-free PET compete, and to soon have the infrastructure to manufacture it at scale. Talk about a game changer. Okay, now let's take a closer look at the potential of weird science at the next stage of supply chain, make. In many ways, this is the heart of operations because it's where stuff actually gets, well, made. For this segment, I want to talk to two people doing very different things, but the one thing they have in common is their work uses biotechnology to manufacture things like mushroom bacon and human kidneys. First, we'll learn a little bit about what bioprinting, aka 3D printing living human organs, what that could mean for the over 100,000 people currently waiting for organ donations in the US alone, from Dr. Anthony Atala.
Organs, when they become available, basically they go into this database where these centers get informed. So when that happens, there's another list of patients who are on the wait list. And it's really, a lot has to do with the match, because the transplant organs that are available are not the same genetically as the patient that you're putting them in. And that's why these patients need anti-rejection medicines. And it has to do with how fast you can get the organ over to that center and whether the surgeons are going to be available to put that organ in. So all of these things go into consideration. There are many ways that you can transfer these organs. Sometimes helicopters, sometimes airplanes, sometimes you can just drive the organ depending on the location. But the main thing is to get that organ as quickly as possible to the recipient. Part of the strategy behind these technologies in regenerative medicine is that you can create these tissues and organs, and by doing so, you don't have to rely on living donors or patients dying to give you that organ, but you can have a readily made supply of these tissues and organs for patients in the future. Just 30 years ago, most human cells could not be grown or expanded outside the body. And so that was one thing that needed to be figured out. The other one was they had to be biocompatible. That means that the cells had to live in a good environment. But then you needed that three-dimensional mold to create the tissues. For these technologies, we're actually taking a biopsy from the same patient, a small piece of tissue, from the same patient's organ. And because we're using the patient's own cells, then there is no risk of rejection. And then using those patient's own cells, we can then grow and expand those cells outside the body and then start mixing those cells with special gels that actually will create the tissue structure that you can then put right back into the same patient. And the process there takes anywhere between 6 to 8 weeks. It also allows you to have a decreased cost because you're actually now automating the process. Really, there's nothing magical about the printer. 3D printing really was just a scale-up tool. Because if you're creating these tissues and organs by hand, you have this variability, this inherent variability that occurs. So the printer does several things. It gives you scalability, but it gives you also reproducibility, the ability to create these structures in the same manner every single time.
It's pretty incredible when you think about the potential for this technology to save lives and how much it will disrupt supply chains in the future. And obviously, this means one thing for the future of medicine, but what could it mean for the future of consumer goods manufacturing? One company called Ecovative might have the answer. Ecovative uses high-tech labs to grow mycelium, aka mushroom roots. Then they use that mycelium to produce 3 different high-demand products: a vegan bacon, a vegan leather, and a fully compostable packaging solution that's similar to styrofoam. Here's Eben Bayer, Ecovative's founder and CEO.
At Ecovative, we're addressing 2 big problems. The first is around industrial farming of animals and the pressure that puts on the planet. And the second is plastic pollution, and predominantly single-use plastics like you'd find in packaging. The three key products we manufacture today is a protective packaging solution, which is like a home compostable styrofoam. Looks like it, you can mold it into shapes, protects things well in transit. But unlike styrofoam, when you're done using it, you can actually compost it in your home garden. It's marine compostable. If it finds its way out of the industrial ecosystem, it's a nutrient, not a pollutant. We also produce products for the food industry, a whole cut meatless meat called My Bacon. We also grow realistic leather-like hides using mycelium to replicate the strength of animal skin. These products are like the triple point for us. They're huge impact if we do them well. The biological processes we use to, say, grow packaging can create positive externalities while it's growing and also in its actual life cycle. So like when a customer gets that piece of packaging, it's not a trash product they're getting. My Bacon addresses the opportunity to solve an important problem, which is both emissions from pig farming and ethics from pig farming. And then lastly, we believe that mycelium is the best technology on Spaceship Earth to go after that solution, which means we can create like a durable business. We use mycelium, which is like the root structure of a mushroom, to literally grow materials. And we either use this as sort of a binder, like how cement and aggregate creates concrete, where we pour mycelium and wood chips into a mold and get a shape. And so we make packaging or building insulation. Or we use these large indoor vertical farms, and we grow these large, basically thick slabs of mushroom tissue. So they could be like 100 feet long, 4 or 5 feet wide, 2 or 3 inches thick. And then depending on the strain of mushroom we use, that slab of tissue could be a delicious whole cut. You slice that up and smoke it and salt it. You've got bacon. Or it could be like a really strong strain of mushrooms, in which case you might slice it the long way and get a 50-foot long sheet of leather, mushroom leather. What we do here is we really take the environments that the mycelium would see in nature. So like in a forest, think of like a cool misty morning at 60 degrees Fahrenheit. There's dew, water droplets on like all the leaves. This is the sort of environment where a mushroom might decide it's going to pop up and make a mushroom. We basically build giant 100 feet long, 30 feet wide, 30 feet tall boxes where we create the environments of a forest like that, and we cycle them ultra rapidly. So the fungus or the mushroom starts to make its mushroom body, and then it dries out. It's like, oh, I'll stop. And then it gets wet again. It's like, I guess I'll start again. And in doing so, it's basically like the DNA contains subroutines as if it was a computer. And these are different subroutines that exist in the mushroom that you just don't typically see in the nature that's outside. One of the fun parts about what we do is you can kind of cheat. Like you can go out into nature and you can see a mushroom like a woody conch growing on a tree, and you can tap on it, you can feel it. You could be like, wow, the top's kind of leathery, or like it's a little squishy. Maybe this would be good sneaker foam. And you can really like pull it off the tree. Some of them are really hard to get off the tree. Like the bark will come with it. Those are good for strong stuff. Like you're taking a clone of a plant. Like, I take cuttings of like a spider plant maybe. You literally just take a cell biopsy. And we bring that back to the lab, and that's how we add a strain to our library. You get to see what it can be in its natural habitat as a mushroom. And then without changing its genes, we change how we grow it, and it produces for us a totally different type of biology. And so we're using microprocessors and pumps and fans and electrons and all this sort of remnants of the last century to coax biology to do this next more advanced thing. On one end of our facility, wood chips and soy husks enter. These get cooked and inoculated with the mushroom cells we've captured from the forest. So this sort of complex of cooked wood chips and mushroom cells is then put in a sort of a tote or a carrier by a robotic handling arm. Every minute, it's stacking up pallets and pallets of these intermediary steps. And you could think of this as concrete that's getting ready to set. Like you see a mixer going down the highway. This is like the precursor material. Those pallets of living material now that could be used to grow packaging or used to grow food, then go into the next stage in our process. Those same containers will be emptied. Now you're going to have wood chips that have been colonized with mycelium cells. So they've sat for about a day and the mycelium has grown through and around those particles. It'll all get broken up, mixed up, tumbled, and then deposited on a conveyor belt that's 100 feet long that goes into a vertical farm. And so that 100-foot long conveyor belt is like a bed of soil, if you will. And then the slab of mushroom tissue will grow above that bed over the next 10 days in this temperature-controlled environment. Each room contains 10 or 12 beds, a couple rows of beds. They get loaded over the course of a morning. You close the doors, you wait 10 days, the mushrooms do the magic, they grow this beautiful tissue. Sort of like a reverse 3D printer, it grows up and out of the soil. Little mist droplets are falling on it. We control the wind in the chamber and are sort of like weave these mycelial fibers together into a mass of tissue. Open the doors, the conveyor belt comes back out, and a big saw slices off big hunks of this mushroom tissue. You slice it differently if it's bacon versus leather versus, say, foam plastic replacement. You compost what's left, the sort of starting material, and you clean the chambers and start over. What's really beautiful about our factories is that on one end, we start with wood chips and we end up with these high-value finished products. Ecovative is a microcosm of what happens when you apply next-generation biology to an industrial system and supply chain. So That's true if you zoom out and look at it from our perspective. The factory that makes food today could the next week make leather just by changing the strain of mycelium, because all the technology, the machinery, if you will, is in those biological components. That's kind of mind-blowing. So I really believe that the future of the technology over the next 100 years is biology, and within that, mycelium materials will play a huge role. And so over the last 10 years, we've really tried to open that field up to everyone. So our Grow.bio program sells a bag of dehydrated mycelium from our factory. And you can literally add water to these bags, they'll start growing again. And so you can think about this again as a concrete living material that you can fill in a mold, like a teddy bear or a packaging part or a coffee cup cozy. It'll grow and you can actually make an object. And we sell these kits inexpensively, 15 or 20 bucks on our website. And the idea is kids, designers, students, teachers start playing with these. And we see a ton of cool projects coming out of that. And then we ladder up. So you can, from that program, get licensed to create your own little business, or you can actually get a license in tech transfer to start your own company. And we've seen folks form companies, like companies growing coffins now, home compostable coffins, and they're doing quite well, selling hundreds of thousands of dollars of coffins each month. We've created initially programs for big brands that pay money to access the product, but simultaneously we've created cooperatives that students and designers can join so that everyone can have access to these early materials at the same time. In terms of how we work with companies, the packaging, food and ag, and leather-like textiles are kind of our core verticals. There's some other listed on our website, but we typically engage with brands first in sort of a foundry program. So we'll look in our research libraries to see if there's a mushroom that sort of solves the problem they need as a material, and if it aligns with our other scale-up efforts. If there are, we often ask brands to invest and partner with us on development, and then ultimately bring products to scale together.
Ecovative is just so cool. I love how they're building an entire sustainable supply chain all in one place, and how they're proving how useful mycelium can be. You can grow it almost anywhere and use it to manufacture almost anything. The only thing Ecovative isn't doing, yet anyway, is actually moving things from one place to another. Which brings us to the last stop on our weird science supply chain tour. MIT reports that freight transportation is responsible for 8% of global greenhouse gas emissions, and its carbon emissions could double by 2050 if action isn't taken. And while we hear a lot about EVs, electric vehicles, and AVs, autonomous vehicles, our last guest says the future of emissions reduction in trucking and shipping really comes down to being able to scale fuel alternatives like green hydrogen. This is Tyler Cole, host of FreightWave's Net Zero Carbon podcast.
I got into the space by starting in freight and logistics. I worked at a company that had 50 trucks, had a chance to do some managed freight for a customer, and we went with the natural gas trucking fleet to try and pilot some new technology. Very quickly saw alternative fuels as an opportunity to differentiate our service. And from there, I just went down the rabbit hole of what's available, how can we do this? I just became to believe more and more that we need systems change happening in how we're decarbonizing long-haul freight and logistics. And there's half a dozen very, very serious ways to do that today. It's just not at scale. Power to liquids technology is super exciting for a lot of reasons. One, you've got a lot of capital investing in technology. You've got a lot of policy supporting carve-outs for demand side, as well as policy supporting production on the supply side. All of that has happened in the last 6 to 9 months, so it's very recent. And I think that that is an area of compound annual growth for the next 15 years that will surprise a lot of people, because there are few other ways to decarbonize some of these sectors like aviation and maritime. From a supply chain officer standpoint, most of the time we don't really, beyond the fuel surcharge, it's all diesel. We don't really care. And we're familiar with that because we put it in our own vehicles at the same type of stations. When we start thinking about different ways to fuel, we're getting there with an understanding of how electrification works and charging. But when you get to some of these other solutions like natural gas or hydrogen or renewable diesel or biodiesel or ethanol, like all these other solutions are different and require some degree of modification, either in charging or infrastructure or fleets. Raw vegetable oils, used cooking oils, things like that go through a traditional refining process and get treated like you would a barrel of crude, and they end up being a drop-in replacement. So chemically identical drop-in hydrocarbon is the goal, because then we don't have to change over the fleets. The technology for capturing carbon has been around for a while. I mean, as part of the natural carbon cycle, we have lots of these that are still working today. Think about agricultural land use, think about the oceans part and natural carbon cycles. Now we've got to start thinking about removing it from the atmosphere using more technical means. And there's lots of different approaches to that, from engineering biomass to capture and store more carbon in the soil, from advanced weathering for rocks and minerals, putting coatings on different sorts of rocks and minerals that can then absorb carbon and store it as part of their chemical makeup. The one most people think of is direct air capture. And direct air capture is enormous fans sucking ambient air through what you might view as like a solvent kind of sheet. So we're pulling air through a very thin layer of membranes that have particular attributes that can capture carbon, so sorbents or adsorbents. And then the carbon stays in, the rest of the air blows through, and then that carbon is stored, and we can either take it, heat it up, release it, we can take it, bury it, we can do lots of different things with it at that point. We have a big CO2 market globally that's super important. I mean, every carbonated beverage, think about it in dry ice, how that's used to preserve things, and medical use cases. Carbon, CO2 and oxygen that gets split off of that is hugely used in medical supply chains. So now we're introducing this demand for carbon to either make fuels or make products. The process to make power to liquid fuels or electrofuels takes captured carbon and green hydrogen and synthesizes them through a couple different processes to get that liquid fuel. It's important when we're talking about hydrogen as a use case to decarbonize that it is green, as we would say, and there's lots of different colors. I think it's less helpful to get caught up on the colors because all they signify is really production technology and pathway and feedstock. You have blue, green, gray, purple, pink, depending on the energy source and where it's coming from. What really matters is this concept of life cycle carbon intensity, because if we're starting with something that's polluting, even by stripping hydrogen off of it, we're using energy in that process and we're not getting any greener. If we start with energy that's made from renewables, so wind, solar, hydro, maybe even nuclear, and we're using that to electrolyze water, for example, so you take water, you put it through electrolysis, which is a process that separates the O and the 2 in the water molecule. You end up with oxygen and hydrogen, and then you can take that hydrogen, store it, transform it, and use it in other processes. If we're doing that with a molecule that's already dirty, it's not going to provide the environmental benefit we're looking for. So there's a very, very big billion-dollar industry starting to take shape around electrolysis and green hydrogen that people are paying close attention to because it has so many good use cases, whether that's industrial heat, whether that's power supply, backup power storage. People are using it in fuel cells to power transportation. People are using it in this process to create power to liquids, drop-in hydrocarbon fuels. It's a very, very exciting time, but it's important that as we use hydrogen and scale it up, that we make sure that it's being produced cleanly. I think this is interesting because it's a disruptive technology. It's a technology that gets people excited. And I hope it's a technology that gets people excited long enough that it catches up to the interest quickly and we can start to scale supply.
What Tyler said about finding a solution that doesn't require modifying fleets is so important. I think that's the key to really making this work for the huge companies that we work with who are trying to find solutions that actually work within their complex systems. The real question then is how can we properly scale these solutions so that companies can use them to power their freight operations? And something else Tyler talked about, carbon capture, has me thinking, what if we recalibrated the way we look at carbon? Hear me out. Really interesting concept from Bill McDonough of the Cradle to Cradle Institute. He calls carbon that has escaped our operations fugitive carbon. It's gone off. We don't know where it is. It's not adding value. We already do this, of course, with the materials and often resources like water that go through our operations, but not normally with carbon. Most of the time we think about carbon as a bad thing. It gets out into the air, it's making everything go cattywampus, we've got floods, it's not great. So instead, we can start imagining carbon as an input. It's valuable. And now some companies are already starting to build sneakers out of it. Somebody's using it to make vodka, quite a party. And what we can do in supply chain is really start imagining the markets around carbon. And I don't mean offsetting market, because that's like a whole nother podcast that we're going to need to sort out. But I mean, imagine using carbon as the valuable input that it is. And if we assign this value to it and can figure out how to watch it flow through our operations, and whenever it becomes fugitive, we can capture it and sell it. Carbon capture is, of course, just one way we can address these issues. Everything we explored in today's episode, along with other newer innovations we haven't even heard about yet, are going to be critical to getting us to where we need to be. But it's also important not to wait around for science alone to save us. After all, hope is not a strategy. Instead, we need to learn how to use this science efficiently and effectively if we want to give the innovations we explored today the best chance to succeed in our operations. After that, it's up to us in supply chain to do the work so that it can save itself and hopefully the world in the process. All right, friends, there you have it. That's it for Radical Reinvention Episode 2. Thank you to Tom Van Aken, Dr. Anthony Atala, Eben Bayer, and Tyler Cole for being our guests, and to 0100's head of research science, Colin Gilbert, for helping us bring some data to life. You can find out more about our guests and the links referenced throughout the episode in the show notes. 0100 community members can also check out the full interviews and our extended conversations online at 0100.com. See you next time.
This episode of Radical Reinvention was produced by Deborah Dahl, Mike Silverman, Sam Anker, Annie Burns, Nick Heineman, Taka Zen, and me, Victoria Marin. Colin Gilbert contributed research insights for the episode, and it was mixed and mastered by Ko Takasugi Chernovin, who also composed our theme music. To find out more about 0100 and to check out our content library, go to 0100.com. If you're interested in joining our community of contributors, send us a note at hello@0100.com.